Alright guys, let's do it. So we are gonna set up our environment and I'm gonna walk you through what we're gonna do with this exploit. I'm gonna use hack system extreme vulnerable driver. It's a kernel driver. It has a lot of vulnerabilities on it and we will learn how to exploit it basically. How to exploit the easiest vulnerability basically. So I wrote some notes here. I am also sharing all these in my blog post, so you can just go and have a look there. But for now, we're just gonna see how we can actually do it on action. I already have my machines, but for the sake of simplicity and to follow up everything, I'm just gonna create it from scratch. God bless us. So let's go for it. I'm using a Windows 7 32 bits machine. Just continuing. I'm not using easy install because it creates problem when I try to install VMware tools. So I'm just going to continue like that. I'm customizing the settings always. Let's call it debugger 2. I'm going to change the settings. I'm generally using auto detect, bridge network. For hard disk, let's not kill my machine. I'm not that generous. Let's change that a bit. That's just a test machine, so it should be fine. Apply. And then let's change the RAM a bit. Maybe 2 GB. That's better. All right, that looks like it. So that's the first step that we're gonna do. We're gonna set the debugger machine. We're gonna set it up in a way that we're going to configure it in a way that we can later clone it to a debugging machine as well. I've been preparing for OSEE for more than a year. I'm getting closer to being ready. I didn't realize that how far I came because, of course, I'm so far away from where I want to be. But I remember how much trouble I had when I was trying to even set up the environment. So hopefully this helps some people out there that are trying to set up their environment to learn kernel exploitation. So let's see. All right, enough with chit chat. I'm just doing basic installation of Windows 7. There are other videos that I'm working on. I'm gonna publish them all together on YouTube. They're not all on Windows 7, so we need to bypass some of the protection mechanisms. So that's why we're not gonna use Windows 7 all the time. It's just for the sake of simplicity for the first video. Let's see, just easy installation. I'll skip this part quickly. So let's have a look on the setup machine that I created already. Let's start it up. And so for now, you're not supposed to know that. We're normally just supposed to start with Windows 7. There's no other driver option that's supposed to come in a normal scenario. So let's see. So what I've set up on this machine is I'm generally having like a VMware. First of all, I'm installing like the VMware tools. Like I said, if you do easy install on a Windows machine, that doesn't allow you to. It creates problems later, so that's the easy trick that you can follow. Then I'm generally creating like, let me show you here, with the sharing, I'm like creating a folder here on my desktop, which I'm sharing with these vulnerable machines later. So in here, I have like a bunch of folders. So what I've done is, let me show you. Let me also show you what I have on under C. So in order to have compatibility later with Windows Debugger when I'm loading the symbols, what I'm doing is I created this folder says extreme vulnerable driver, and under the compile folder, which I created again, I put this driver. If you go through the same path, you should have the same on your C folder. Besides that, I also put like the driver in here so that it can load all the functions and everything else in Windows Debugger later. So that's what we have here. What I've done is I also install IDA Pro. Oh yeah, let's go back to our checklist here. If you follow these, I installed WinDebugger with VDK, OSR loader, which you can see in here. IDA, I'm using very old version of IDA Pro, IDA free. it's either pro, it's just either free, because it's the newest version is not compatible with Windows 7. So that's something to keep in mind when you do your research. You will find all of these online already. Cool. So what else do we do? So we're going to computer properties, right click. I'm sure that you will still like spend some time trying to figure things out, but I don't know. I think this would help me if I would see everything on a video. And there's environmental variables, and from there I edit this environmental variable. Just copy and paste. I am sharing all these in my blog post, or you can find it anywhere if you check how to set up HEVD driver or any other vulnerable driver. Cool. So then we are rebooting this machine. If you want to test if the debug symbols are working, we can do that. Let's do it together. We're doing this, and let's open an executable. It should be under system 32, calc exe. Where are you, calc exe? Here we go. I'm just loading this one. Just copy and paste these comments that I'm writing in my blog post to see if everything is working. That's the easiest way to verify. So at the end of the third comment that I'm writing here, it should not give me any error messages if everything worked properly. And as you can see here, it looks all alright. There's no error messages that I'm seeing. That's cool. So what else are we doing in debugger machine again? This was very confusing for me, like over a year ago when I was trying to set up machines, and there's a debugger machine and a debugging machine. What's going on? Which action I need to take? So first of all, we are setting up everything on the debugger machine, and we will do all the dirty work in here. And we will observe if we get a blue screen or if we are like getting a anti-authored system shell, etc. on the debugging machine later. Cool. So what else we're gonna do before we create a debugging machine? We're going to cmd exit command prompt as administrator, and we're gonna write the following comments like this. This is basically the part that we are creating the driver. When you reboot the machine, it will ask you, do you want to start as Windows 7 or as this? So then what you're doing is you're copying this and the value from here that you get in here. Sorry, mark. In here, you're copying this and you're saying this comment, and then you're checking if everything is all right. We can do it already. I don't need to do it double. Oops. Could not copy, could we? BCD edit, debug settings. Everything looks alright. This is serial and the port number is looking fine. So what do we do then? We are shutting down this machine and we are going back to our VM there. I'm right clicking and saying linked clone to create basically the debugging machine. Let me move this guy here so we can see it better. But we need to do a configuration, quick configuration here. I'm right clicking. Right now I don't have a config option, right? In my Mac, I don't know how we would do it on a Windows computer, but this is like a Mac I'm using. If I click on option, it shows up open config file in editor. I remember how much pain I had with this. Most of the blog posts that I was reading was about a Windows computer, and I'm using a Mac forever, so that was painful. Anyway, just look for serial 0. Should be here. Yep. So you should have something like this. In the beginning, I had something like Tink line or something. I needed to change some stuff. Again, in most of the blog posts, this is about Windows, so you will see like backslashes and stuff. If you're using a Linux or macOS, that's what you're gonna do. For serial, you can change to whatever name you want. And for the debugger machine, we need to get server for this parameter, while for the debugging machine, let me go there, right click, click on option button, and this will appear. Let's go to serial, and as you can see, I changed this to client. So that's the only difference that I do. Okay, let's go back to our manual. Then we're gonna try to connect. So I'm going back to my debugger machine. It's already on. Let's shut it down. So let's do everything properly. I'm assuming that Okay, what is that? Okay, let's assume that we follow these configuration steps, and then what I'm doing, I'm starting my machine. It's gonna ask me how do you want to start it, with HEVD or Windows 7. I am starting as Windows 7 on debugger machine all the time. We never follow the HEVD driver that we just created with this bcd edit comments on debugger. We only do it for debuggy. Okay, it sounds like I speak Latin or something. Cool. So we just started it. Okay, there are some dirty files that I created here. Anyway, what I'm gonna do is I'm gonna start Windows debugger. I'm gonna go to kernel debug, go into com, checking these values if everything is the same as we saw from bcd edit comment. I'm going there, I'm starting it, double click, make it full screen, waiting to reconnect. Right. On the debugging machine, we are gonna start it up, and it's gonna ask us how do you want to start it. We're gonna say with HEVD that we set up on the original machine before, like the debugging machine is just a clone. I can turn this off now. As you can see, there is some stuff happening on the right side. Okay, that looks better. Let's see everybody at the same time in this way. Okay, where are we? We're attempting to connect right now. We started the debuggy, and then we're gonna test the connection. When you look like that, like the formula is not so big, you're just going step-by-step guide, but yeah, if you just started it and if you're getting an error, but that's a good thing, no? That's the beauty of learning something by yourself. You have to have problems, you have to have troubleshooting a lot, and you have to read a lot. I don't know how many times I read through different functions of Windows API, and it will never end, I'm pretty sure. Right, some stuff happening here. I'm gonna break in here. That's also another thing. You can just go debug, oops, and break, control break it says, right? But again, in my Mac, I could not figure out which button is break, and I'm using like a German keyboard, and it's not my mother language, so it makes everything so messed up. So what I've done is I just went to VMware Fusion and I created like a shortcut Control P for control break basically, but it must not exist for your computer. So just be aware, you can just create a shortcut for that if you don't want to go to here and break all the time. So that's the thing. Let me go there and let me break here, and we're gonna run this comment. Cool. And I'm gonna say sim noisy before I say reload all the links. Let's wait. Loading kernel symbols. It's gonna take a while. When we are running this command lmmh, once we connect these machines by using OSR loader, when we load the driver, basically it should show us in this comment. So what we're gonna do is we cannot do anything on the debuggy right now because this is saying busy. Oops, wow, okay. So if you want this debuggy to be able to continue, that's the thing that we need to do. G, that means debuggy is now active. Let's run HEVD right now because I already set this up. I'm just going to show you if you're doing it for the first time how it's supposed to happen. We're running it as administrator, and you're going to your folder which was under C something. We're finding this under vulnerable folder. This is file. I'm opening it. We're changing this for automatic. Let me stop the service just for now. Normally it's not how it's supposed to. If you're doing this for the first time, we're going to that folder, we're changing this to automatic, we're saying register and start the service. As you can see, we see the HEVD in here. Everything is supposed to be alright in here. So what we're gonna do, so that was a setup. If you came here so far and you see the screen, it means everything worked. there's another troubleshooting that I can show you guys. Again, I break in here. I'm saying LMMH to show all the modules that's been connected already. I'm going to HEVD. If you see browse all global symbols, it's supposed to show like that. If it says it could not load anything, that means when you look in here, C hex system vulnerable, there's this like directory or like the path in here. If it does not exist on your computer, you have to go back and create this folders and make sure that you have all the corresponding files under this. So that was one thing that I had in the beginning, so that's something to keep in mind. Make sure that you have that one working for you. I did not publish the blog posts yet, but when you check this video, probably I already published this on YouTube and also the blog post in my blog, r100.it. But for now, I'm just showing you my original blog in my OneNote so that we can just follow up easily, because there is a lot of theory in here. I don't believe that this is a video that I can actually squeeze into minutes, but I will try to keep most of the stuff for you to learn. I will just like walk you through so that you can like follow up easier. This is not like a course or part of a course or something that you can follow to learn how to do kernel exploitation, because it's something that you really need to dedicate your time. It doesn't work like I just like watch a video and learn it in 10 minutes. It won't happen. Okay, enough of chat. Let's jump into what's going on in here. So if you follow the previous video, we set up our environments. We had debugger machine and the debugger machine. They're both Windows 7 and 32 bits. So I included some theory in here, which will be needed later. Most of these are wrapped up from the most popular blog posts or from Microsoft's API documentation. So don't expect like this content to be 100% original, because I learned from others. So that's one disclaimer. So let's see what we have in here. So for device drivers, there are kernel mode objects, and we cannot touch them directly from user mode. So if you want to test them, if you want to debug them, etc., we cannot use them from user mode, right? So we need to like work around this. And so how do we do it? We do it through something called handle. This is like intermediary solution. You can call this a proxy if you want. So via handle, we can actually communicate with kernel drivers or device drivers, which are kernel mode objects, from user mode. So how do you create a handle? This is one of the Windows functions that we're going to use in this exploit and also in the future exploits, create file A, which allows us to create a handle, which we can pass later to another Windows API function that we will use, which is device IO control. If you look at the first parameter of device IO control, which is handle, this comes from the other function that we're going to use initially, which is create file A. So we're going to get the symbolic link. If you go through the source code of this, of this driver, or if you debug it via using IDA, which we will do in a second, you will realize that this is the symbolic link for this driver. We're going to pass this later for LP file name, so that's why this is important. And I also mentioned it in here. Cool. So again, some theory. After we obtain this handle to the device driver, then we will utilize IOCTL, IO control codes via IRPS, IO request packets. So again, there's this Windows API function, as I mentioned, device IO control, for user mode apps to communicate with the kernel mode drivers. So obviously, we need two Windows API functions for this exploit: create file A to create the handle, and device IO control to pass the handle and do more stuff, which will come in a few minutes. Again, the first argument that I mentioned will be the handle to the device driver that we create via this function. And these control codes are sent to specified driver via IRP. We will see this. What does it mean soon? So just read it through yourself. I don't want to talk about so much theory in here. Just a few things to know. Device IO control and create file A are both located in kernel 32 DLL. Alright, so after learning like few API calls and what we're gonna use it for, let's go through the source code review. Again, I'm just gonna show you like my notes in here. It's easier to follow. Okay, I wrote this wrong. So I'm gonna use the 2.0 version of hex system vulnerable driver. The file name may differ for you. Let's see, what do we have in here. So if we go to driver, let me see. I was using the 3.0 first, then I changed it to 2.0, so hopefully the names are properly written here. I did not write something wrong with it or something. Probably I did. Anyway, so if you go to not Overflow stack, but Stack Overflow C, let's open this with Sublime to see what is that. Let's see. Okay, this screen looks very crowded right now. Sorry about this, guys. Let me like turn this on again. Bring this up. Yeah, so let's read this first, then read through the source code as well. So what does it say? There's RTL copy memory routine, copies the contents of a source memory block to a destination memory block. So let me see what's going on here. So we're including this H file. Obviously there's some content here that we need to grab from. And then there is trigger stack overflow vulnerability, trigger stack overflow function. It gets user buffer and size. It passes some information here. Then we have if-def secure function. If this function is called, then this RTL copy memory function, RTL copy memory routine as mentioned in here, takes kernel buffer, user buffer, and compares the size of your user buffer with the kernel buffer before it passes it to kernel buffer. However, in the vulnerable version, as you can see here, trigger in the stack overflow, we're just passing the size of the user buffer just as it is. So of course this causes buffer overflow vulnerability if this is called. So that's where vulnerability exists. The author is already explaining it in a perfect way. So if you want to know more about what this routine is, RTL copy memory, and what's the proper usage, as you can see already in here as an example, but you can also go and refer to the documentation from Microsoft. Alright, we're like passing an exception if needed, and then there's Stack Overflow IOCTL handler. So we will have this IOCTL handler for every single one of them. I'll try to explain that in a bit. For every single vulnerability that we have in here. So that's how they program this. So there's also the Stack Overflow IOCTL handler function. So let me see, I also explain it in here. So if the correct IOCTL code makes it to the IOCTL handler, there's a user buffer and a size parameters. They are ready already here, and trigger stack overflow function will be triggered with the size of the user buffer directly without actually comparing with the kernel buffer size. So that's the vulnerability, and that's like the source code review if you have access to the source code, but we should also have a look at it from at IDA later, IDA really soon. So we're gonna do some analysis with IDA. Oh my god, this is so small for you guys. Let me try to make it bigger. So let's see, on the debugger side, let me make this smaller. Oops. Alright, so we're going to IDA free. Yep, very old version. We're going there, and we're gonna load the file in here. I'm opening that. Yeah, do the heavy lifting, whatever. Let me make this a bit bigger maybe. It's easier to see in this way. And full screen here. Cool. What I'm generally doing is like text view first. And then I'm generally checking for functions. The IOCTL handler function that we talked about. Let me sort this guy. All right, this is All right, IRP device IOCTL handler. So we're going to look at this function, which basically handles the IRP requests with IOCTLs. So I'm going to double click on this. If you do this, go into the function and say graph view, you can see that it's all right. This function is basically going through a lot of other functions, because this is the main function that manages all the IOCTLs. So that's one thing to keep in mind. You can also click on escape to go back to where you were. That's another thing to keep in mind. I'm going back to text view. It's easier to read in this way. Okay, that's better. So yeah, you can also follow the blog post. I also try to explain more there. So let's see what we're gonna do. As I explained, I was using HEVD 3.0, then I changed it to 2.0, so some names are mixing. Let's try to focus on here first. So as you probably know, an IDA, when the subroutine starts, it starts like this, like a bit of comment, and then IRP device IOCTL handler starts here. So as you can see, it's another subroutine here, so we don't need to like go to a different place. So if I scroll down a bit, as you can see, regularly it's calling a different function or a different subroutine, like call this arbitrary override, Stack Overflow GC, and Stack Overflow IOCTL handler. So that's what we're trying to achieve, right? That's what we are interested in. Let me double click on this Stack Overflow IOCTL handler, and it triggers Stack Overflow. I click on trigger Stack Overflow. As you can see in here, if you remember from the source code that we went through, it was comparing the user byte. It was comparing the size of the user buffer with the kernel buffer size. And as you can see here, we're seeing that we're passing byte numbers in here. And it's 800 hex bytes, which is 2048 bytes in length for kernel buffer. So anything that we pass more than that will cause a Stack Overflow vulnerability. Okay, let me go back with escape. So where were we? I will go back one more time. So if you remember, that was IRP device IOCTL handler. So every single one of them is calling another IOCTL handler for another function, which triggers another function to trigger a vulnerability, basically. So what do we see in here? For Stack Overflow IOCTL handler, I'm seeing a function in here. Whether you can double click on it, or you can see like these lines, where do they go up? If 155FB that I'm looking for. I'm just gonna go back a bit to see 155, and that's the beauty of IDA. If you just like click on it, it just shows you the other occurrences. And what I'm interested in is in here, so the earliest appearance of this function, basically. So what does it do? So we move ECX to AX, and then there's subbing this value from AX. If 0, we are jumping in this function, and all this triggering happens for the Stack Overflow vulnerability. So what does it mean is that the previous value before jump 0 has to be 0. So sub AX whatever value has to be 0. That means AX has to be 0. And we are passing ECX into AX, and that means, and that's the part that we actually detect the IOCTL code, which will trigger the Stack Overflow vulnerability. So we will do the exact same thing for other vulnerabilities as well. Let me go through it one more time to understand what did we just do. The easiest way to do it is go to functions, find the function that basically does all the IOCTL handler thing. This is the start of it, subroutine, start of the subroutine. If you scroll down a bit, it shows every single IOCTL handler routine that basically triggers another vulnerability and calls another function. We're seeing this one, Stack Overflow IOCDL handler, and this is happening in this function, log this one. If you scroll up a bit, or if you just follow these arrows, you're seeing it in here, jump 0, this one. If the value of the previous instruction is 0, short jump, do a short jump to this location. So we are just going back to there for this Stack Overflow vulnerability. Okay, I scrolled down so much. Anyway, so I'm just looking at the previous instruction and I'm getting this value as the IOCTL handle. Cool. So I'm going to show you very quickly IOCTL handler. Let me show you in the text view first. That's going to be easier. What we're doing is Stack Overflow IOCTL handler, double clicking, which triggers Stack Overflow. So if I go to graph view from trigger Stack Overflow, that's like the bigger picture. So we have Stack Overflow IOCTL handler, it goes in some way, and if it's triggered with jump 0, then it's triggering Stack Overflow function, which basically allows us to have this overflow. Otherwise, if not 0, goes back here. And this is what we referred to with IOCTL in the previous analysis like a minute ago. Cool. Like I said, you can just check my notes. They are more in detail. I'm just trying to show it in action very quickly. So what we're going to do is that we're going to have the blue screen of that. Let me show you the exploit that I wrote first of all. I guess that should be this one. So this looks very small, I know, but I tried to make it as easy as possible. So we're just like using some Python import, and also we're using C types instead of using a C code. We're like going to use Python with these. I'm just loading like Kernel 32 as both of these functions are using Kernel 32, create file AA and device IO control. So I'm just going to use that. If you remember the syntax of create file AA, create file A, you will understand where these values are coming from. These are basically starting from here to here. And LP file name is supposed to be this. But since we're using Python, we need to like double these backslashes. I'm not gonna dive into detail. It's just like how the syntax is supposed to be. It's just like error handling here. If we cannot get the device handle, or if we cannot connect with the driver, then we're gonna EIP overwrite with the length, and then the 42s, 442s needs to be an EIP, and then the rest is basically filled with C's. There's also the device IO control function, API call. Again, we're just gonna put the handle here, as we mentioned. This is the IOCTL that we got from with the IDA analysis, and the rest is basically coming from here. Some people like wrote some codes with explaining all these, like where this is coming from, but you can find it in my GitHub code or also in the blog post, so I'm not going to dive into details for these. So what I'm doing is, okay, let's get blue screen of that, right? Alright, so let's kill IDA. We did analysis already, don't save database, goodbye. I'm going to Windows Debugger again. Let's do G so that it can run on the debugging machine. Alright, I'm here. So what I'm gonna do is I'm gonna go to my command prompt. I'm gonna change it to yeah, I did not put a environmental variable for Python, so I'm doing this miserable act right now. But yeah, it makes it more exciting for if it's gonna work, right? Oh my god, I'm really miserable right now. Alright, so I'm gonna do it for S3PY, which is the same thing that I had here, just named it differently. So if you run this to verify, this should help us. We are seeing the EIP value overwritten with 42s, EBP is overwritten with 41. That looks like a Stack Overflow, that's nice. And we need to pass through the crash. We'll pass the exception by going to debug, go unhandled exception, and I'm gonna click on G, which will give me the blue screen. I don't know why, guys, but it relaxes me. I like it. It's destructive. It will restart the box now. So yeah, let's talk about what we're gonna do after that, because if that will be a normal user land scenario that we're trying to exploit the Stack Overflow vulnerability, that will be all right. So that's the bad news. We are just starting. We did not do anything so far, actually. So the experts already expect you to go through this by closing your eyes and do the real shit after that. So if you were thinking that was so hard, I'm sorry, I have to break it to you. We just started. All right, enough with chit chat. So what we're gonna do, we're gonna use a technique called token stealing in order for us to go to enter the system, because we already assume that we are on a box, but we are trying to exploit a vulnerability on the kernel driver to go to enter the system. So in Windows, as you know, each process has their own access token. Basically, it specifies the security content or context of the process that runs it. And we will try to steal a token for a process that already runs with enter the system privileges in order for us to be successful at the end of this exploit. So we need to steal that token that runs with system privileges and copy it to a target process. Can be command exe, why not? We can get a command problem this way. So if you go to the original code from Hex System Extreme Vulnerable Driver, they're so nice. They even gave us like a payload to basically talk about the syntax. So, okay, our blue screen is back. Blue screen guy is back. So yeah, there's like the syntax for our payload. And if we know these offsets, basically we can just use this little code for us to steal a system token. So how are we gonna do that? It looks very complex, I know, but let's assume that we already have this. Let's assume that everything is like blue sky, we're happy, and we already know this. We just need to figure out how to find the offset. I mean, it shouldn't be so hard because the guys already gave us this, right? So all right, I know that you guys are like not so familiar with this, but we will just learn how to basically figure out things in here, all right? So we're gonna learn some things in here by using Windows Debugger. So the first thing is, maybe I should show you the roadmap, which will make all these lines very, or least complex. So what we're trying to achieve is we're gonna start enumerating KPCR, then KPCRB, and then K-thread, which are all connected to each other, and then E-process and active process links, or from E-process to token. So if you know that we're gonna go through that, it makes it easier. So, or like keep this in mind, or like paste it to Sublime or something. Let me do it actually for you. Maybe it will make it easier for you to understand, guys. Believe me, I was confused in the beginning too, but then you memorize what's going on and do it in your sleep. So yeah, let's see. Okay, I'm going back to the real work. What's gonna happen here? So the KPCR are beginning point, right? This stands for Kernel Processor Control Region. This is another tier course on kernel. As I did, please just go and read the documentation to understand what these are and why are they useful. I'm just like showing you the action part. So basically KPCR, it stores the various information that outlines details about the CPU. Cool. So this is our entry point in order for us to reach out to active process links and token. So let's see. How are we going to look into the data structures within KPCR and their offsets? The offsets are written in here and the data structures are written in here. So we're going to just do it. Copy that and go back to, okay, let me change it a bit. I'm trying to like show you guys on my screen at the same time, but it looks ugly. Okay, let's stop this by with control break, or we can also go to debug and break. So let's start enumerating the data structure under KPCR. So starting. All right, we are back after reloading symbols. So I'm just looking at data structures within KPCR with the following comment. So what we were looking for was KPCRB, KPRCB, sorry, if you remember. And as you can see here, it's plus 120 bytes offset from KPCR. Good to know. It's 120 bytes away. So from that, we are continuing to, it's like an inception, looking into more things. Oh yeah, RCB, not, I always do this mistake. And yeah, as you can see, that's a lot of data structures here that we can check. If you scroll up a bit, be more than a bit, okay. All right, that's a lot. Okay, KPRCB here. And if you look from 4 bytes away, we are finding K-thread. If you look into our original scenario, how we're gonna look, it's not that crazy. So let me also copy and paste this information that I'm gonna show at the end, which will make everything easier. So for K-thread, which is in here, 4 bytes away from KPRCB, and KPRCB was 120 bytes away from KPCR. So that makes it 124 bytes away from KPCR for K-thread. So that was the first value that we get. Then we're gonna check for eProcess. So we just continue enumerating in the same format and the same syntax, right? We check for K-thread, we just did some analysis, nothing crazy. We're checking for eProcess after that. And the same syntax, we're looking for DT, NT, K-thread. Another one with a lot of data structures. So if you scroll up a bit until KD, as you can see in here, so if you scroll down a bit, it's 40 bytes away from K-threads. So we were looking for cup state, so we're looking for KPC state, and from that, one step away is going to be eProcess. Again, I'm just looking for it, and if you look in here, eProcess, K-process is 10 bytes away from KPC state. So if my math is correct, 40 bytes plus 10 bytes is going to be 50 bytes. Awesome. So the next one we're going to look at is going to be active process links and token, and they're going to be from eProcess, so it will be easy because that's the last step that we need to follow. Again, this is not the video that I'm going to explain all the theory. Come on, it should be fair a bit. This topic is hard enough itself, so you should just go learn all this theory yourself, do research as much as you can. This is basically just the part that I'm walking you through, while assuming that you already know what you're doing. So for active process links, it's, let's see where it is. If I scroll down a bit, it's here with B8. And the token is on F8. Cool, we found these all. I'm just noting down all these values, as you can see in here. A, B8, these are just offsets so that we can use it under this token stealing script that we already have, all the syntax that we already have. So one more thing that we need to do is we need to check for processes that runs with system privileges. So if you look in the first one, it already runs with system. Okay, once it's done, you can see the process ID in here. So we are just gonna run the following comments in order to get the token value as well. Right, if I see it in here, the token is also mentioned there. Perfect, we got all the information that we needed. We're just filling this information, the offsets as given in the previous syntax, nothing crazy. After that, we're gonna also have a very small, so that's the final status with the offsets that we found. Just fill the blanks basically after we do the enumeration with Windows Debugger. So how are we gonna get the system shell? So let's see what's going on in here. I put them in different colors for us to catch up easily. So the buffer part is the same, just adding shellcode instead of EIP 42. This is the same, given the handle to device IO control and creating handle in the beginning. These are both included in kernel 32. Cool. This is like the handle error message that we got. So what do we add in here? So the only thing that we add is this token stealing payload that we are adding in here. We just fill this using the offsets that we found during this enumeration with Windows Debugger. After that, we need to assume that the dep is, we need to bypass the dep, and there are like a few lines of code that's very easy to understand. We're using virtual alloc and RTL memory functions. If you want to get more information about that, you can also refer to the Microsoft's own API documentation. Again, I'm not going to explain all these. Refer to the blog post if you need more information as well. So there's nothing crazy actually. You're just adding the payload by using the enumeration skills that we already had. Just adding a few lines. We will do the exact same thing for the others as well. So try to understand what this means. We're bypassing virtual alloc. We're bypassing dep with virtual alloc, and then just adding the shellcode next to the offset that we found. And nothing crazy. We're just opening CMDX after that. So let's see it in action. I mean, why did we do it so far otherwise? We got the second one. As you can see, we use create file A to create the handle for the driver, allocate an RWX region by bypassing dep, copying the shellcode to a newly allocated RWX region, and opening a brand new shell as enter the system. That was it. So yeah, I know that the topic is very hard, but if you are already on your way to learn kernel exploitation, I'm assuming that you already know most of these theory, already suffered enough by reading other people's blog posts, figuring things out yourself, try to set up your own environment many times. Don't worry, we all went through that, at least what I've seen from blog posts so far, and I can assure you that I went through the same thing. So just try harder, do it yourself many times, set up your environment, troubleshoot as many times as you can, and get a beautiful shell at the end of it, and try to understand every single line. And yeah, hopefully you enjoyed the video. See you in the next kernel exploitation topic video, guys. Cheers.